We're starting the third chapter of the syllabus, third worksheet to be precise. The heading is forces and moment. We're going to talk about equilibrium cases and how we can achieve equilibrium and how moment can be further used for our benefit for calculation and for observation, so on and so forth. One of the first idea that actually was covered within these two figures is that if in any case an object is supported by multiple different horizontal supports, for the case of considering the balance situation, we can consider any of these supporting point as a pivot. Having said that, it means that if you consider this point as a pivot, it means that the object is considered to be rotating about this contact point. So which means if we apply enough weight over here, enough force over here, and that force produces an enough anti-clockwise moment that it can actually lift up the object of the other end, this object can start to rotate about this point where this end goes up, this end goes down, having this point as a pivot point. This is possible. Vice versa, that one is also possible. So this is one of the key aspect of balancing situations, that if we have multiple different support points, we usually prefer to consider the support points as our prospective pivot points for the calculation. The next figure over here actually is a normal object drawn without any support point. So if you consider an object that is suspended in space, maybe International Space Station, or for a satellite that is going around the Earth within a specific orbit, if you don't have any specified support object for any specific support point for an object, in those cases, usually objects tend to rotate about their center of gravity. It means that if I try to show this in a figure, if you have an object that is of, let's say, this much shape, and the center of gravity of this object is right over here, if we apply a force that is aimed directly towards the center of gravity, somewhat like that, this is gonna cause an acceleration of the object without making it to rotate. So you're not gonna have rotation, you're not gonna have moment, you're gonna have acceleration, linear acceleration, that is. But if we apply a force that is offset of the center of gravity point, let's say if I apply a force maybe somewhat like this, so consider this force is no longer present, so forget about this force right now. If we apply a force maybe somewhere like this, which is definitely not going through the COG, in that case we're going to have a bit of moment produced on this object, and that's going to also cause the object to move forward, which means this force is going to cause the object to have some acceleration in this direction, and at the same time this object is going to start going anti-clockwise rotation. So it's going to rotate and fall down, in this case down, because I've drawn a vertical downward force. But that's the example for the case of a freely suspended object. Freely suspended object tends to orbit around or produce their moment around their center of gravity. These are the two different cases that we need to remember in our head, because that can come useful whenever we are considering the effect of forces for disconnected bodies. The other thing that is important over here is that conditions of equilibrium. Okay, there are two conditions for equilibrium. The conditions are very simple. The two conditions in very simple terms can be written like this: that first condition for equilibrium is that resultant force should be zero. The second condition is the resultant moment should be zero. This equation can be further extrapolated in terms of if we want to go by the component division. So we can say that the resultant sum of the horizontal forces should be zero, resultant sum of the vertical forces should be zero, their total sum should be zero, or the individual sum should also be zero. What I mean is that if we have multiple objects, if we have let's say we have a force over, if we have an object over here that is subjected to multiple different forces, let's say F1, F2, F3, blah blah blah, and everything, and the question tells you that the object is at equilibrium. Now if the object is at equilibrium, and if I name all of these forces, let's say F2, F3, let's say there are a number of forces working on the object. This would mean that the vector sum of all of these forces, so F1 vector plus F2 vector plus f3 vector plus f4 vector plus dot, 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 plus fn vector. If we do the vector sum of all of these forces by means of a polygon rule, for example, we're gonna get 0, which means if the object has to be in equilibrium, the resultant should be 0, or the polygon should be a vector polygon should be a closed polygon. Or vice versa, we can also say the other way, that if the polygon that we get out of the vector sum of these forces is a closed polygon, then we can decide that the forces individually produce an equilibrium as well. So it can work either way. The next thing is that if we have all the forces produce equilibrium, it would mean that if we divide the forces in the individual components, for example, if I take the horizontal component of F1, horizontal component of F2, horizontal component of F3, and if I add up all the horizontal components, that should also be individually 0, which means that resultant in the horizontal direction should be also 0. Resultant in the vertical directions should also be 0. If you sum them up, that would also be 0 because they are individually 0, which this actually goes on to mean that the f1x plus f2x plus f3x plus dot, 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 plus fnx. So all the horizontal components should add up to 0. And similarly, all the vertical components should add up to 0. So this is a way to solve the problems in a much simpler fashion, which can help in a lot of different cases. And also, for an object to be in equilibrium, we need to have resultant force 0, and we need to have resultant moment to be 0, which means anti-clockwise moment should be equals to clockwise moment. If any of these two information, any of these two logic is not fulfilled for an object, maybe both of them are simultaneously unfulfilled, or maybe at least one of them is unfulfilled, then the object is said to be not in equilibrium. So the object might have non-resultant zero force, non-zero resultant force, or it might have non-zero resultant moment, or maybe both of them are non-zero. So the object would be said to be not in equilibrium. Which brings us to the scenario that it is possible for a moving object going around, having a bit of a rotational spin can still be in equilibrium. Try to think about it. The example that I just gave you a little bit earlier, let me extrapolate this example. Let's say this example over here. Let's say this is a celestial body. Maybe let's consider this as a free rock meteorite moving down in space. By some propulsion mechanism, by some rocket or by some bomb, let's say we push onto this object, and that applied a force onto this meteorite, let's say for 1 second, with a large amount of value. For the duration of 1 second, this meteorite would experience a resultant force, it would experience a resultant moment. Once this application of force stops, try to understand, once this application of force stops, this object would once again return to zero equilibrium force and zero equilibrium moment. But the object would keep on moving in a straight line while spinning on its own axis about its center of gravity. So if an object is seen to rotate, it doesn't necessarily mean it is under the effect of a resultant moment. A visibly rotating object could have been under the effect of a moment which started the rotation, but it doesn't necessarily have to be under an effective moment currently right now, because if you have an object that is experiencing a moment right now, it should speed up the rotation. Try to think about it. If you have a freely suspended object that is experiencing an ongoing moment on itself, which is not stopping, it's working, so every single second the moment is going to cause the object to speed up or spin faster. So point to be noted, visibly moving rotating object can be in equilibrium provided it doesn't experience any resultant force, it doesn't experience any resultant moment. Momentum, it doesn't experience any resultant moment. Momentum is a different thing. Sorry, I messed up. So these are important aspects to keep in mind. The other thing that we have over here is actually showing us that we can calculate the moment on an object applying on a single point by two different methods. I'm going to draw up these two methods for you to make sense. One of the things that we have seen in our O-levels scenario is that if we have an object over here, we have a defined pivot point right over here, and if we apply a vertical force with the object's alignment, let's say if this is a 90-degree and this is our distance d, the produced moment is given by fd. That's pretty simple. However, if we have the force applied at some angle, we need to go for some bit of a uh, different bit of a more drawing. For example, if the force is applied over here at a direction that is this, where this is the force applied, and the distance that is given is from here to here, this is our distance d. And if in that case we have to draw up a perpendicular line over here, uh, so that this is producing an 90 degree over here, and if this angle is theta, then sorry, not this angle, if this angle is theta, I mean if the force produces an angle theta with the axis of the object, then this length should be d sine theta. So that way the moment produced should be force multiplied by perpendicular distance of the force from the pivot point, which should be m into f, m equals to f into d sine theta. So that can also work. The other thing that can be done, other than undergoing this whole drawing and everything, other than finding out the component of the perpendicular distance, that is d sine theta, we can also divide up the force as well. So that's the important new thing that we have over here, which is a much more simpler process than this one. Is that, let's say we have an object over here which has a defined pivot point right at this point, and we have a force that is working on the object that goes in this direction, which is F. Now the defined distance that the object has from the pivot point to the application of force point, let's say that is d, and the angle over here is theta. So other than actually finding out the perpendicular distance like that, what we can also do, we can divide up this force into two components. For example, this F force was shown in this manner, so I can actually draw up the align component like this. Let's say this is our F cos theta component, because this is the adjacent component, and we can have a vertical component that looks somewhat like this, which should be our F sin theta component. For those of you who are having a bit of a difficulty to understand how this worked, I can show it to you in a very much simpler way, that if F is over here and theta is over here, I could have also drawn the F right that, and the angle over here can be also considered theta, because this angle, I mean earlier this angle was defined as theta, so on alternate side this should be also theta. So if this is F, so this is our F cos theta and this is our F sin theta. I just drew the F cos theta and F sin theta starting from this point. That's basically what I did. So this is also another way to represent the forces. So the vertical component of force is F sin theta. You have to see that F cos theta is working directly through the pivot point. So the perpendicular distance for F cos theta component with respect to the pivot point is 0. So this one will not produce any moment whatsoever. However, the F sin theta component would actually produce a significant moment, which can be calculated by moment equals to F into d sin theta. So that's also another way that other than drawing up the whole force thing, we can directly find out the, sorry, I actually wrote it wrong. I should have written it like this, that moment can be calculated by F sin theta multiplied by d. So that's also another way to go ahead and calculate the moment for forces which are not perfectly producing 90-degree angle with the designated distance that is labeled in that question. The next one that we have is vector geometry. Vector geometry is very simple. R equals to P plus Q. Triangle rule, components are placed one after another. Parallelogram rule, components are placed from the same point. So triangle rule can be shown like that. If we have two vectors P and Q, we just place them one after another. R gives the resultant. You know how it works. I'm not bothering to show you this figure. But one thing that is important that is just shown up over here. If you're trying to find out the difference of two vectors, or if you're trying to find out the subtraction of two different vector quantities, we can go by this. Let's say Z vector is given by P minus Q, which can be represented as P plus minus Q. So if we can find out the resultant vector of P and minus Q, that should be equals to Z. So that is one way to represent this. The other way to represent this thing is that if you change the side of Q, this can also show that Z plus P should be equals to Q. So this figure, I mean the vector geometry figure for this equation can be shown in two different ways. On the figure that you can see over here, we are trying to find out the resultant of P and minus Q. Have a look in this figure. We have the P vector over here. And earlier Q was defined upward right like this. Here minus Q was labeled as downward left with the same length, but in the exact opposite direction. Parallel orientation, but working in the exact opposite direction, that gives you minus Q. So P, at the end point of P, we are starting minus Q. So P plus minus q gives you z. In this case, this is the equation that is coming from z equals to p plus minus q. This is the equation which is defined by this part. Or we could just revert this arrow sign and get rid of the minus. That's what is shown over here. So this figure and this figure are exactly same. Have a look. We flipped the arrow direction and got rid of the minus sign. This figure basically tells us that in this case z and q are the sequential vectors, which means z plus q gives us the resultant p, which is also what is wrong in here. বলবান এখানে একটু এডিট করো, এখানে একটু লেখা ভুল আছে. This should be z plus q equals to p. The side change was a bit mistaken. How can I edit this? Can I edit this?
Sir, z plus q to p.
হ্যাঁ, মানে এই সাইড চেঞ্জটা লিখতে ভুল হয়েছে.
স্যার এটা কোশ্চেন আছে স্যার.
বলো
স্যার এটা ইররিলেভেন্ট স্যার, এটা রেকর্ডিংটা অফ করবেন.
তাহলে ক্লাসে পরে বলো, মনে রাখো.
জি স্যার.
I'm just doing a bit of an overriding here because I don't know how else to do this. Editing PDF is not easy because the whole point of a PDF is that it's not supposed to be editable.
Sir, I guess you should save this, otherwise your edited file will be lost.
Yeah, I will save this right now. So I just saved it right now. So the equation is a bit messed up. So please correct the equation. The figure is perfectly all right. The figure should look like that z plus q should give us the resultant vector p, which is shown up over in this figure, which is a perfectly understandable figure. So both of these figures pretty much represent the same thing. In your actual answer choices, if they are trying to ask you that which of the following vector diagrams represent z equals to p minus q, they might give you this figure, they might give you this figure. So you have to be smart enough to be able to manipulate the given equation or manipulate the given figure to find out the appropriate correct answer. So that is a required capability that we have to develop.
Sir, are the the diagrams all right, sir?
Diagrams are perfectly all right. Yes, the equation was slightly messed up.
Okay, sir.
Diagrams are gonna. Okay, then the new thing that we have available in a syllabus is what we call a couple. Now, couple is a very what can I say, very specifically defined thing. This is how we define a couple. Two equal, parallel, and opposite forces are called a couple. Do you understand? Two equal, parallel, and opposite forces are called a couple. And there is one thing that is missed over here, is that couples should be somewhat apart from each other. I'll show you what this means. You can write over here that you can write use a small bracket, and you can write that they should be offset of each other. Offset, OFFSET. Let's say irregularly shaped object. If we have on this object two forces applied which are equal in magnitude, parallel in alignment, opposite in direction, and not working in the same perfect line. So their alignment should be perfectly parallel, but they should not working in this exact same lines, which means that they do produce a bit of an different line of action. In these kind of scenarios are what we call them to be couples. And these two forces doesn't have to be applied on two sides of the center of gravity. That's not necessary. It's very much possible that if you have a, let's say you have a rectangular object that looks like this. You have a rectangular object that looks like this. If it's an uniform object, obviously you do guess, you can guess that the center of gravity should be somewhere located over here. A couple can very well work one force over here and the other force working over here. That is also a couple. It doesn't have to work on two opposite sides of the center of gravity or two opposite sides of the pivot point. As long as these three conditions are fulfilled, that we have two equal forces, parallel forces working in opposite direction, and they're not working in the exact alignment, which means they're a bit offset from each other, they produce a turning effect on the force, and that turning effect is what we call couple. Coupler calculation could be interesting এই জন্য বলতেছি দেখো, if we have the distance between the two couple is given by, let's say, d, and let's say individual forces are given by F, the torque or moment produced by a couple is given by F into D, not 2F into D. You might wonder why. The reason is that we can calculate the you can actually calculate the moment that a couple actually produces on a certain object in a lot of different ways. So we have a lot of different examples that we have on this thing. I'm going to explain this figure part by part, so try to understand. Before we jump into this calculation, there are multiple things which is defining is that in many cases the word torque is used, in many cases the word moment is used. Both of these words are exactly same. Torque and moment are exactly same words. The way the grammar works is that typically the word torque is used for couple. For example, the phrase the torque of a couple is more common than the moment of a couple. So the word moment is usually more associated with a single force, whereas the word torque is usually more associated with the couple. But if we flip them, for example, if I say that the torque of a force or the moment of a couple, they're perfectly okay and perfectly correct. So that's the part that you shouldn't mess up. Torque and moment, they are both exactly the same thing, so we can use them interchangeably, no big deal. So this question this part over here shows that torque is represented by a symbol tau. Tau is the Greek letter which looks a little bit like this.
স্যার টর্ক অফ ডাবল ফোর্স হবে না স্যার, দুইটা ফোর্স যেহেতু?
না, কেন হবে না সেটা দেখাচ্ছি। What is the symbol of tau? This is how it looks like. Yeah, this is a T with a little bit of carved leg, like that, slightly carved leg. So that's that, and this is the figure for the couple calculation. আচ্ছা, এই ফিগারটা এক্সপ্লেনেশন আমি তোমাদের নেক্সট ক্লাসে বলবো না, পার্ট বাই পার্ট, and we'll continue on from this point. Many kids have left, so I might as well call it a day. So I'm stopping.
স্যার তো